Hello everyone, welcome back to another class of regeneration, and we will move on to a new topic that is on liver regeneration, and we will study the signaling events. And liver regeneration, as I already told you, that is the only complex organ that is capable of regeneration in mammals, whereas lower vertebrates like fishes and frogs can regenerate pretty much every organ. So this picture you can find in pretty much every liver regeneration literature. That is the picture of Prometheus. It's a Greek legend character who was punished by gods for giving fire to humans because he used to be, Prometheus happened to be a lover of humans, and as a punishment his liver will be eaten by an eagle whole day, and the next day it used to regenerate. And it's quite interesting that this character is stayed back in humans also probably as a continuation of the blessing or benevolence we got from the god Prometheus. So the compensatory regeneration is the one terminology used to describe the liver regeneration, because it never regenerates the lost part, rather it compensates for the bulk. Today, the standard assay for liver regeneration is partial hepatectomy, where some lobes of the liver are removed. Liver has got, it's a multilobular structure. Although the removed lobe does not grow back, the remaining lobes enlarge and compensate for its loss, and it will gain in bulk. So such compensatory regeneration is basically the division of differentiated cells to recover the structure and function of the injured organ that has been observed in mammalian liver and in the case of zebrafish heart, etc. So liver regeneration, if you look closely, you can see the regeneration of the liver occurs by two major mechanisms. So the first mechanism is the proliferation of the existing hepatocytes. Hepatocytes are basically the parenchyma of the liver, that is the major workforce of the liver is the hepatocytes, and the repopulation from the progenitor cells. These are the two approaches the liver regeneration does. Human liver regenerates by proliferation of the existing cells. The liver cells do not fully de-differentiate when they enter the cell cycle, nor there is a regeneration blastema. Blastema is a group of undifferentiated cell that is formed at the site of injury or amputation. In the case of salamander or axolotl, etc., such a blastema never forms in the liver. So the mammalian liver regeneration has two lines of defense. The first one being the mature adult hepatocytes. They are normally not dividing. They are terminally differentiated. They are in G0 arrest. Are instructed to join the cell cycle. That means enter into the cell cycle and proliferate till they have compensated for the missing part. If 1 gram of liver is removed, the hepatocytes will divide until it restores the lost quantity. Not in the same place, but somewhere else. So there is a population of hepatic progenitor cells that are normally quiescent but activated when the injury is severe, and the adult hepatocytes cannot regenerate well. And due to senescence or alcohol or any other, say, viral infection or any other disease or liver cirrhosis, etc. So normal mammalian regeneration, there are 5 types of cells exist in adult liver, namely hepatocytes, ductal cells, fat storing cells, endothelial cells, and Kupffer macrophages. So these are the main 5 types of cells, and all begin to divide to produce more of themselves, because you need all of them, although the hepatocytes are the predominant population. Each cell type retains its cellular identity, and the liver retains the ability to perform its function. Remember, if the liver is damaged, there is no blastema that is formed, and the existing cells, while performing its liver specific duties, it will continue to proliferate also, such as the functions include the bile acid synthesis, albumin production, toxin degradation, etc. Even if you are brain dead, even if the brain of a person is not working, you can make that body surviving it by putting the person in ventilator. But if the liver is down, you don't have a machine to put in. So technically liver is one of the most complex organ in your body. means more important in terms of functionality than brain, because there is no replacement organ available. You can't put a heart lung machine. You don't have a ventilator for liver. So if liver is down, the patient cannot move forward. Several pathways may initiate liver cell proliferation, and the end result of which downregulate and it's not totally suppress the genes required for the differentiated functions. Some genes are induced that will allow them to proliferate while retaining its liver specific functions. And the cell will continue to do its job, and the cell, while activating these genes required for proliferation, and the bulk is built in this way. Proliferation of hepatocytes following partial hepatectomy is the most studied model of liver regeneration in humans. Resection up to 90% of the liver, 70 to 90 on an average, but a maximum of 90%. So if your liver is around 1.5 kilo, you can remove most of the liver, retaining around 150 gram liver. It will bounce back, it will grow back. Liver can be corrected by proliferation of the residual hepatocytes. When you donate liver, sometimes you may have seen between relatives, you donate a liver. Only a small piece will be taken from the donor and it will be given to the recipient, and the liver will grow in that host. Hepatocyte proliferation in the regenerating liver is triggered by the combined actions of cytokines and polypeptide growth factors. There is involvement of immune system, which we studied in the previous class. There has to have a proper immune response. How is the injury to the liver sensed in order to trigger the regeneration? Someone has to tell. There is no CCTV camera to watch. So when there is an injury, someone has to sense it. What is that molecule? It is very interesting to follow. The removal or injury to the liver is sensed through the bloodstream, and there are some liver specific components that will be leaked into the bloodstream. That means it can be bile acid, it can be some of the liver specific. Otherwise, if liver is damaged, there is no point in kidney regenerating or some other organ regenerating. So it has to be liver specific factors that are lost, while others such as bile acids and gut lipopolysaccharides level will increase. Gut lipopolysaccharides are supposed to be controlled and kept in check by the liver, and if it is not happening, you may have seen in jaundice, the person's eyes will become yellow in color, skin will become, nails will become, all will become yellow in color because the liver is not doing the duty. And these are indications for the liver to start proliferating and growing back in bulk. These polysaccharides induce some non-hepatocytes to secrete some paracrine factors. Paracrine factors are the factors that will allow the neighborhood to respond in a given way. They are some of the signaling events that induce the hepatocytes to enter the cell cycle. The Kupffer cells secrete interleukin 6, one of the pro-inflammatory cytokine, because they are similar to that of macrophages. They can secrete IL-6 and TNF-alpha, tumor necrosis factor alpha. While the stellate cells, they can secrete hepatocyte growth factor, also known as HGF, hepatocyte growth factor, and another factor called TGF alpha and TGF beta, transforming growth factor alpha, transforming growth factor beta. The specialized blood vessels of the liver, they can also produce HGF and Wind2. Wind2 is a ligand of Wind signaling, which is essential molecule for the cellular proliferation. As you can see in this picture, it is basically a sinusoid. That means basically a cavity of the liver, sinusoid, which is lined by endothelial cells, and also there is a Kupffer cells, and also you have stellate cells, and also the neighboring hepatocytes. So one hepatocytes will be primed by the Kupffer cells by secretion of interleukin 6 and TNF alpha, and this Kupffer cell in turn will prime the neighborhood Kupffer cell, neighborhood hepatocytes to enter into the cell cycle. And so the neighboring hepatocyte is priming, and the stellate cell also is releasing HGF and TGF alpha to the same hepatocytes, and now it is primed. So it was in a G0 arrest stage, now it will enter into the G1 phase. And also note, the extracellular matrix is capable of releasing some of the growth factors such as TGF alpha and HGF. And all these together will make hepatocytes to enter into the cell cycle. However, you don't want unwanted proliferation. So the cell, the hepatocyte which entered the G1 phase now is acted upon by TGF beta, which is one of the anti-proliferative molecule, similar to that of the brake in a car. So you have accelerator, the moment you lift the accelerator, you need to use brake if you want to reduce the speed of the car. So the TGF beta tells this hepatocyte not to go. This doesn't mean that the proliferation is inhibited. The proliferation is happening at a reduced rate. So the same stellate cell telling, in one hand, it is telling the hepatocytes to enter into G1 phase. The same stellate cell is releasing TGF beta and telling the same cell not to proliferate. So this allows a controlled proliferation and it will get into G1 to S, and the metabolic pathways also has to continue and it will enter into the mitotic phase. Like that, you will generate the bulk of the hepatocytes and as a part of liver regeneration. In first, the priming phase, the cytokines such as interleukin 6 are produced mainly by the Kupffer cells, and they act on the hepatocytes to make the parenchymal cells competent enough to receive and respond to the other growth factor signals. In the second phase, the growth factor phase, that is the first phase is the priming phase, second is the growth factor phase. The growth factors such as HGF and TGF alpha produced by many different cell types do that, and they act on the primed hepatocytes, okay, not the normal hepatocyte, primed hepatocyte, and they stimulate the metabolism and entry the cells into the cell cycle. And the last phase, that is where the hepatocytes, they are quiescent and it takes them several hours to enter the cell cycle, and they progress from G0 to G1. Basically both are same phase. G0 means it will not enter the cell cycle, G1 means it can proceed to S phase and then G2 phase and then M phase. Almost all hepatocytes that is of the parenchymal type, they replicate during liver regeneration after partial hepatectomy. Not that area alone, because that area is not the one which is going to be replaced. The entire liver has to respond and it will become bigger. The wave of hepatocytes replication is followed by replication of non-parenchymal cells such as Kupffer cells, endothelial cells and stellate cells. So they continue to contribute, they continue to proliferate. However, that is a second wave because the major bulk player is the hepatocytes. The second number or represented are the Kupffer cells, endothelial cells, stellate cells, etc. So during the phase of hepatocyte replication, more than 70 genes are activated, that is contributing to this priming and the proliferation. These include genes encoding for transcription factor, cell cycle regulators, regulators of energy metabolism and many others. They contribute to this. And now comes the final phase, that is called the termination phase, where the hepatocytes return to quiescence. Quiescence means coming back to G0 phase. This is what happens. Hepatocytes still connected to each other in the epithelium cannot respond to HGF. Then if so happens, how is regeneration is triggered? So what we should understand, if a given scenario, does every hepatocyte is capable of responding to hepatocyte growth factor, and it will work only on primed or only when there is a damage, then this response becomes interesting. Let us see how this is regulated. The hepatocytes activate a gene called c-Met. c-Met stands for the receptor for HGF. HGF is a ligand, it is a secreted molecule, but everyone cannot. Say satellite is releasing a signal from the space onto your house, but you cannot watch the TV. You need to have a dish antenna and a TV. Dish antenna and wire connected to your TV, then you can watch. Otherwise, you can't watch. So the c-Met acts like a receptor or like a dish antenna for receiving HGF. Within an hour of partial hepatectomy, the c-Met is induced. So those cells which has got c-Met can now respond to HGF. The trauma of partial hepatectomy may activate several metalloproteases. Metalloproteases are enzymes that is doing a scavenging job or a cleaning job. Say for example, you are entering a room or you are entering your own house. Your house is full of furnitures. So first you should clear the furniture so that you can open the door and put your foot inside. In your living room, there are 2000 chairs are put. How are you going to enter? So this damaged area, the clearing job is done by the matrix metalloproteases that digest the ECM. What is ECM? Extracellular matrix, and permit the hepatocytes to separate and proliferate. Otherwise, every cell is anchored onto extracellular matrix, and that has to be cleared so that they can be free. They can be a free bird in order to proliferate. Metalloproteinases also cleave HGF into its active form. HGF usually secreted in an inactive form as a precaution, as a protection, and the HGF now is acted upon by these proteases or proteinases, and it will become a active HGF which can bind on to the cement. Together, the factors produced by Kupffer cells, endothelial cells and stellate cells allow the hepatocytes to divide by preventing apoptosis. If apoptosis is called cell death. If apoptosis is occurring, the number will decrease. If your mother is making dosa, every dosa is made, you are constantly eating, then end of the day the plate will be empty. There won't be any dosa. So, at least mother should stop you from eating for at least 10 minutes or 15 minutes so that there will be at least 1 or 2 dosa in the plate. Same logic applies. So, apoptosis will be prevented because you need to increase in bulk. And this is done by activating cyclins D and E, which will help in increasing the proliferating and repressing the cyclin inhibitors such as P27. So, activators are turned on, cell cycle activators are turned on, and the inhibitors are turned off. Both are needed. So, proliferation of non-hepatocytes in the liver typically lags that of the hepatocytes by a couple of days. Non-hepatocytes means the non-parenchymatous tissue. That means the cells which are doing a supportive role, like stellate cell, Kupffer cells, endothelial cells, those kind of cells. They lag behind by a couple of days, with the result that the small clusters of newly produced hepatocytes take form before they interact with other elements of their liver to reconstitute the normal internal hepatic structure. Because if all cells are dividing at equal phase, every cell is dividing, then end of the day, each one will have 1:1:1:1:1:1. You don't want that, because the majority, the bulk, around 30-40% of the total cells type belongs to hepatocytes. So less is known about what brings the cellular regenerative ability in the liver to halt. But one major molecule is TGF-beta, produced by the stellate cells, is known to inhibit re-entry of the hepatocytes into mitotic cycle. So the same stellate cell is allowing the primed cell to enter from G0 to G1, and the same stellate cell is releasing transforming growth factor beta to stop from continuing to be in that phase, because this is a check and balance system of cell proliferation. In some situations of chronic toxic damage to the liver, such as alcoholic cirrhosis or repeated exposure to carbon tetrachloride, or hepatocyte regeneration is not sufficient. Hepatocyte regeneration will be sufficient when the damage is minimal. If the damage is severe, it is not sufficient to prevent the fibroblast cells within the liver from producing the connective tissue scarring. This will lead to a scar formation, and the liver is not going to regenerate properly. There is a junk region that will be created in the liver, and the regeneration will be compromised. As you can see in this picture, this is a cross section of normal hepatic lobule, and this is a larger area. You can see there is a portal triad is there, where you have hepatic artery, portal vein and bile duct acting together. And you can see whenever there is an injury that occurs, injury to the cells, and injury here in the right hand side, you have injury cells and matrix, injury to the cells and matrix. Here you can see the matrix, like you can see like a chamber here, it is intact, and the cells are kind of damaged. They are not looking healthy, as you can see here. They are damaged. However, the proliferation can continue, and then this normalcy, as you can see here in the right hand top side, it is restored back because the matrix was intact. Here what happened? Injury to the cells happened. As you can see here, cells are rearranged, but the matrix is not there. Like you can see here, matrix is properly, here there is no matrix. Then what happened? The matrix is non-existing, then the regeneration is not proper. See how many hepatocytes are formed here? Here hardly any hepatocyte. They regenerated, but meanwhile the matrix have given rise to scarring. That is called a repair by scarring. Scarring is nothing but abundant production of the extracellular matrix, which is mainly done by the fibroblast tissue, which is not a tissue specific cell, which is basically glue type of or gluing type of cell. So liver regeneration from the progenitor cells in situations where the proliferative capacity of hepatocyte is impaired or inadequate, such as after chronic liver injury or inflammation, the progenitor cells in the liver contribute to the repopulation. So moderate damage, hepatocytes will take care, but if there is a severe damage, the liver stem cell or liver specific progenitor cells and stem cells are more or less the same, they contribute. In rodents, these progenitor cells have been called oval cells because of the shape of their nuclei. They are oval in shape, and some of these progenitor cells reside in a specialized niche called canals of Herring. They are located there where the bile canaliculi connect with the larger bile ducts. We have a picture here. You can see here. This is basically what you are talking about. This is the hepatic artery, and you have plenty of hepatocytes, which is brown in color, and this canals of Herring, which is labeled here. You can see these yellow colored cells. They are basically the hepatic progenitor cells. They will come into picture if the damage to the liver is severe. There is an extensive damage has happened, then they come into picture. Say for example, the liver size became 150 gram like I mentioned earlier, or you received a new liver, a donor. That situation, the stem cells in that liver fragment has to proliferate. Hepatocyte proliferation alone will not be sufficient. So this is what you should understand. And the stem cells are kind of a second line of defense when it comes to liver regeneration. To summarize the second line of regenerative ability in mammalian liver, you can see if hepatocytes are unable to regenerate, more than unable to regenerate, inadequate is the correct word. Inadequate to regenerate the liver sufficiently within certain amount of time. That means there is a waiting time. Certain amount of time, the second line is activated, which is involving the progenitor cells, which is called oval cells in the case of rodents. A small progenitor cell population that can produce hepatocytes and bile ducts, they start dividing. And oval cells appear to be kept in reserve and are used only after hepatocytes have attempted to heal the liver. So hepatocytes have the ability to regenerate simply because any toxic food or any toxic stuff going into your body, including alcohol, has to be detoxified by your liver. Or in other words, every day your liver is dying. Every day, no matter whether you are consuming alcohol or whether, as long as you are eating some natural product, some toxins present in that will be damaging your liver. Hence, the hepatocyte has to fix it. And the regeneration by hepatocytes is a daily process. And if that one doesn't happen because of type 2 diabetes or maybe fatty liver disease, non-alcoholic fatty liver or non-alcoholic liver cirrhosis, all this situation, hepatocytes fall behind. And intercellular signaling contributes a major role when it comes to regeneration of the liver, and it includes mainly three main pathways. Pathway 1 is called autocrine. What is autocrine? Cells have the receptors on their own for the secreted factor. Say, assume I am a cell, or let us assume a good example to give. I am a cook and I am not giving food to anyone. I am cooking and I am making food only for myself and I don't give to anyone. I will cook and eat. So this can be easily compared to that of autocrine signaling. It do not allow anyone else. Let us assume paracrine signaling. What does it mean? Cells respond to the secretion of nearby cells. That means you can compare to your mother. Mother do not cook only for her. If a 4-member family, mother will cook for her and her family members. And this can be compared to that of paracrine signaling. That means it works in the vicinity. Then comes the endocrine signaling. What is endocrine signaling? Endocrine signaling is essential for a lot of distantly acting. Let us assume a restaurant making food, and through Swiggy or Zomato or any other online distribution system, they are sending to various customers. And this is endocrine system. That means cells respond to factors and hormones. Now I will show the previous picture once again so that you will know much better. Here you see there is lot of hormones coming into picture. That is thyroid hormone T3 and the EGF, epidermal growth factor, duodenum. These are endocrine signal. And pancreas, which is secreting insulin, and adrenal gland producing norepinephrine. Everything, all these factors are endocrine factors that is contributed during regeneration of the liver. And you can see here this individual cell, that is Kupffer cell, that released IL-6, TNF-alpha. This is basically paracrine signaling. And this cell, hepatocytes, is priming the neighboring cell. This is paracrine signaling. And if some of the factors released by the hepatocytes acting on itself, that is called autocrine signaling. This stellate cell releasing TGF-beta and negatively influencing the hepatocyte, that is a paracrine signaling. It is not released into the bloodstream. What is released into the bloodstream are the endocrine signaling. So all three kinds of signaling comes into picture when it comes to the regeneration of the liver. You can see here in this picture, in this cartoon, the cell releases its own ligand, and the receptors are needed for that also. It is releasing and it is acting on the receptors and it is responding accordingly. It can be also compared to that of, you are stimulating yourself. You may have seen sometimes people who are playing sports, after performing well, they will tell, okay, well done man, well done, or you did a good job. You are talking to them yourself, and it's a self-boosting. So this is basically done in the case of autocrine signaling. Whereas paracrine signaling is basically a molecule that do not act in the same cell, but it acts by diffusion into the neighborhood cell. And paracrine signaling is very predominant. Autocrine signaling and endocrine signaling do happen in a routine manner, but paracrine signaling is normally done in the case of liver regeneration very effectively. And endocrine signaling, like growth hormone, insulin, etc., they are all released into the bloodstream. As you can see here, there is a endocrine cells present. They are released into the bloodstream, and distant target cells they can receive. But remember, distant target cells can respond only if it has got the receptor for it. If it doesn't have the receptor, it cannot act. So now some questions come up. How does the liver stop growing when it reaches the appropriate size? Very good question. Like I told you, 1.5 kilo. Who tells? Is there any weighing machine situated inside? How to stop it? And the answer is not known. Having said that, we have some clues. Let us see. One clue comes from the parabiosis experiment. What is the parabiosis experiment? Partial hepatectomy in one of the parabiosed rat will cause the other liver to enlarge. What does it mean? You take the bloodstream of one rat and you fusing with the bloodstream of the other rat. You keep two rats together and connect the blood vasculature of one mouse in one rat into the other rat. That means their circulatory system is now united. Of course, they don't have this blood mismatch issue like what humans have. Even if humans, if it is a B positive with a B positive, nothing should happen, but no experiments will be done in human. In this case, in one rat, the liver is damaged, but why the other liver has to become bigger? This do happen. Some factors in the blood that is released from the amputated liver containing rat is entered into a normal rat's bloodstream to establish the liver size. So Huang and colleagues in 2006, they proposed these factors are to be bile acids. So partial hepatectomy stimulates the release of bile acids in that rat, but since its bloodstream is connected to a normal rat, this activates the transcription factor FXR in hepatocytes and promotes their proliferation. As a result, it becomes bigger. And also understand, the liver hepatocytes have the ability to enhance their size. They will become hypertrophied also. So now we have few questions that is remaining. What are the molecular mechanism by which these regeneration promoting factors interact? How are they interacting? Is there any master regulator? How is the liver is first told to begin regenerating or proliferating? Or we also said that how stem cells come into, or progenitor cells come into picture. They will wait. Who is telling them? How is it being measured? How is the liver told to stop regenerating when it reaches an appropriate size? Say, the moment it reaches from 150 gram to 1.5 kilo, it will not grow to 2 kilo. Who is telling them? How is it being stopped? So these are some of the interesting factors to explore. So we will continue more about the liver regeneration in the next class. Thank you.